Hello everyone, a very warm welcome to the teaching show, and I'm Dr. Poonam Nigam, and in this video we are going to learn something about combustion reactions. It's a very important topic from the GATE point of view. There have been several questions asked on this topic, so we will go one by one and cover all the salient points where you can go wrong during the exam. So let's get started. Let's understand first why we are interested in studying combustion reaction. Usually combustion is of some fuel, okay? So and it gives you energy, and whole economy is driven by fuel, okay? So that's why combustion reaction becomes very important. Okay, so there can be either a partial combustion or a complete combustion. How do you define a partial combustion? Suppose your fuel is not burning completely, okay, and there are some unburnt hydrocarbons left in it, or you are using oxygen which is lesser in amount than the required, and so you form carbon monoxide. Then you say that partial combustion of fuel has taken place. When you have like sufficient amount of air or oxygen, then your fuel completely burns and forms carbon dioxide and water, and that is known as your complete combustion. So in this course, whenever I say complete combustion, you will understand that your products are carbon dioxide and water. Since you have an organic compound which you use as a fuel, say for example your coal, petroleum, anything, so it has carbon and hydrogen. So carbon will burn completely and form carbon dioxide, and hydrogen will burn completely and give you water. Apart from that, because these are the organic compounds which have been formed by burial of organic dead matter millions of years ago, so it also has small amount of sulfur in it. So whenever you burn these fuels like say coal or whatever, it also has some amount of sulfur in it. So while burning, it also gives sulfur dioxide. So apart from these two, you have sulfur dioxide. And if your combustion reaction, it's a highly exothermic reaction, so it also generates a large amount of heat. Sometimes the temperature go up to thousands of degree, okay? So if your combustion reaction is highly exothermic and the temperature goes above 1500 or 1800, then whatever the air you are supplying, in that you have nitrogen. So nitrogen also gets oxidized and forms NO, okay? So at high temperature, you have also nitrogen oxide, fine. So these all are main four components which you find in your combustion flue gas, okay. So what is flue gas or stack gas? Whenever you burn a fuel, whatever the gaseous products which are being formed, that are known as flue gases or stack gases, okay. Stack nothing but it is chimney, another name for chimney. So the stack gases or flue gases, fine. So it has carbon dioxide. Always it happens that partial combustion takes place, so some amount of carbon monoxide, water, sulfur dioxide, nitrogen oxides, plus in the flue gas, don't forget that you will also have some amount of unburnt hydrocarbons. Say if I am burning methane, some amount will leave with the flue gas. Then you will have excess of oxygen which you have supplied. Then you will also have nitrogen which has not burned, okay. So whenever you have been given a combustion problem, always in the flue gases, take care what all components you are including, okay. Now I told you that because all these organic compounds which we burn as fuel, they are very expensive. You know what are the rates of petroleum right now, okay. So these are expensive, and in order to burn them, we always try to burn them completely, fine. So always we use excess of oxygen or air, fine, because air is you are getting free of cost, right. So always you use air for combustion because you get free in air. You don't use most of the time oxygen, okay, which you have to extract from air. There is no need to do that. So what you do is you carry out combustion reaction in the presence of air. For simplicity's sake, in this course we take air is composed of only two components. We know that it has carbon dioxide, some gases like argon and all those things, but we will just club it together and we will say that it has 79% nitrogen and 21% oxygen, and its average molecular weight is 29, okay. So this is the thing we are going to take everywhere. Then whatever the flue gases which are coming out after combustion, usually you try to find out what is the composition of those flue gases. Okay, why do you want to find the composition of flue gases? Because there are certain environmental limitations. Pollution Control Board, it sets up limitations that you cannot emit, like say SO2, it cannot be higher than this much ppm and so on. So you have to analyze your flue gases and see whether they are within the environmental, whatever the limitations which have been set up. Okay, so for that usually ORSET analysis is used. ORSET analysis, if you want a video on that, how you do it, I can make another video. If you want, you can put it in the comment section and I will make a video, detailed video on ORSET analysis. But usually ORSET analysis, it gives you the composition on dry basis. When I say dry basis, that means the water part is not counted in it. Okay, so it will leave out the water part and it will give you the composition on dry basis. I will give you an example. Say for example, the flue gases contain carbon dioxide, SO2, methane, oxygen. Water will be removed out, okay? And then say 100 moles, then it will totally will be composed of methane, oxygen, carbon dioxide, carbon monoxide, sulfur dioxide, whatever, but water will be left out, okay? So that is your dry basis. Now, separate humidity measurements are done in order to calculate your water content, okay? Then whenever you are doing a material balance, you cannot leave out water. Okay, so whenever you are doing a material balance, you have to convert your dry basis to wet basis. Okay, so we will quickly take a simple example. ORSET analysis gives me dry basis. So nitrogen is 65%, carbon dioxide is 14%, carbon monoxide is 11% and oxygen is 10%. On the dry basis, you will see the summation is 100%. Okay, so I have left out water, but separate humidity measurements tell me that the flue gases which are going out, 7% of it is water. Okay, so now in order to convert to the wet basis, what I will do is, because I know the composition, I will take the basis as 100 moles of dry gas. Okay, now if I have 100 moles of dry gas in the flue, okay, that will account for 93% of the flue gases, because 7% is water. Okay, so my dry gas is basically how much? It is equal to 93%, because remaining is water and it is given as 7%. Right? Now this 93% is what? 100 moles. So if my total flue gas flow rate is, let's say, X moles, okay, then 93% of this, so 0.93 of the total flue gases, that will be equal to your 100, right? So what will be the total amount of flue gases which are going? 100 divided by 0.93, and it comes out to be 107.5. So what is happening over here? I have now calculated, if I also include water in it, what will be the total flow rate of the flue gases. Flue gas total flow rate is 107.5 moles. It contains 93% of dry gas, which is 100 moles, and water is remaining. That means 7% is water, and water is how much? So H2O number of moles will be equal to 7.5 moles. Now if I want to calculate my mole percentage on wet basis, what I will do? Okay, so nitrogen, I will write down all the components, and then you will see it's very easy. How many moles of nitrogen do I have? 65. So 65 divided by 107.5 into 100, that will give me, this is CO2 is 14. Okay. CO is 11. So I'm just dividing it by total number of moles and multiplying with 100. So that will give me my mole percent. And remaining is water. If of course it will come out to be 7%, but you can do the calculation and again and see whether you are right. Okay, so this will give you, now you have calculated your mole percentage based on the wet basis where your water is also included. Okay, you can do the calculations and see the summation comes out to be 100%. Fine. So this is very simple. If you have dry basis, you can convert it to wet basis. Vice versa also you can do. That is much simpler. Suppose that these are, let's write down these values. Okay, so I am going to write down what is the mole percentage of all these. This is 60.5%. This CO2 is 13%. This is 10.2%. This is 9.3%, and of course this is 7%. Okay, so suppose I have been given a reverse problem. This is my wet basis composition and I want to convert it into dry basis. Now what I will do? I will again choose a basis for this as 100 moles of total flue gases. Okay, then it will have nitrogen 60.5 moles, carbon dioxide 13, CO 10.2, oxygen is 9.3. Okay, water I will leave out. Fine. And then what I will do is that just add all these and then you find it out. Let's do that. Reverse problem. Okay. So I am now going from, this is my wet basis to dry basis. Okay. Now I will choose again 100 moles, not 100, okay, 100 moles of this whole thing, flue gas. Okay. Then it has nitrogen, that is equal to 60.5 moles, carbon dioxide, that is 13 moles, carbon monoxide, this is 10.2 moles, and oxygen, that is equal to 9.3 moles. Okay, you add all of them, whatever is the summation, fine, that will be the total number of moles. Let's call this as whatever the total number of moles. Okay, then in order to find out my mole percentage, what I will do is 60.5 divided by total number of moles into 100. So I am now converting it into my composition based on dry basis. Okay, so I hope you understood this, and now we will move to another important concept, which is percentage excess of air or oxygen. Okay, so I told you, because these fuels, they are expensive, we always want that they burn completely. In order for them to burn completely, we usually supply excess of oxygen or air. So there are few terms which are described. One is theoretical oxygen. Okay, let's take an example. Let's say CH4 is burning. Okay, and I am using oxygen to burn it. Right? It can give me carbon dioxide plus water, and also if it is not burning completely, then it will give me carbon monoxide. Okay, so theoretical oxygen is based on complete combustion of your fuel. So when you are calculating theoretical oxygen demand, what you are going to do is that you are going to assume that this burns completely, so as to form carbon dioxide and water. You can quickly balance this equation. Okay, so 1 mole of methane requires 2 moles of oxygen to burn. So if you have 100 moles of methane which is burning, your theoretical oxygen required will be 200 moles of oxygen. Okay, there may be some problems in which they will say, okay, one more reaction is taking place, CH4 plus 3 by 2O2, that is giving me CO plus 2H2O. Okay, and they may also say that, okay, the amount of CO2 to CO formed is, say, whatever, 7:1, or they can give this type of ratio and then ask you what is the theoretical oxygen. Don't get confused. Theoretical oxygen, by definition, it is complete combustion of your fuel. So even if they have given you this reaction, they tell you how much carbon dioxide and carbon monoxide is formed, don't go and try to calculate how much oxygen is required for this and how much oxygen is required for this. That will be wrong. Whenever they say what is the theoretical oxygen required, you always base it on the complete combustion of the fuel. So forget about this reaction. Okay, so whenever you are calculating theoretical oxygen, always base it on the complete combustion of the fuel, that is, you are getting the end products as carbon dioxide and water. One more thing you have to keep in mind, sometimes these are very simple mistakes you might do, okay, during your exam. They can also say 70% of methane converts. Okay, that doesn't mean that if they are supplying 100 moles of methane, you go and find it out for 70 moles how much oxygen is required. No, you have to base it on the complete conversion. Whatever is going in, we will assume that whole of it burns. That is your theoretical oxygen. Okay, so even if they say 70% burns, you're not going to base your calculation for theoretical oxygen on 70% of the amount which is fed. Okay, so these are the two general mistakes which people do while calculating your theoretical oxygen. Okay, now usually oxygen is not supplied, we are supplying air, so we usually call it as theoretical air. Okay, so how much is theoretical air which is required? That air which contains theoretical oxygen. Okay, now we know that oxygen, let's say, I will say nitrogen to oxygen ratio. What is nitrogen to oxygen ratio? That is 0.79 upon 0.21, or it comes up to be 3.76. Okay, so 1 mole of oxygen is present in how many moles of air? Let's say total number of moles of air will be 3.76 plus 1 equal to 4.76. Right? So 1 mole of oxygen is present in 4.76 moles of air. So whenever you have theoretical oxygen, you have it, then theoretical air, simply how do you calculate it? Let's say theoretical, I'm not going to write full thing, let's say theo air, that is equal to 4.76 times your theoretical oxygen. Okay, just to speed up on your calculations, remember this theoretical amount of air which is required, it is 4.76 times your theoretical oxygen which is required. Okay, and one more thing you have to keep in mind, that let's talk now about excess air and excess oxygen. So we have already seen what do you mean by percentage excess. We used to say amount which is fed minus the stoichiometric amount divided by the stoichiometric amount. Over here now what we are talking about, percentage excess of oxygen, that will be the oxygen which is fed minus the theoretical oxygen which we have calculated based on the complete combustion of the fuel. Okay, so O2 fed minus O2 theoretical divided by O2 theoretical into 100. That will give you your percentage excess, or if I just miss this 100, then it will give you fractional excess. Okay, let's say that my fractional excess I am going to refer to as F now. Okay, so I am saying this is my fractional excess. Okay, now from fractional excess you can quickly find out what is the amount of oxygen which is fed. Let's do that. If you rearrange this equation, O2 which is fed, now that becomes equal to 1 plus F times theoretical oxygen. Okay, so if I say 50% excess of oxygen, let's say I am giving 50% excess of oxygen, that means my fraction is 0.5. Okay, so now then it becomes 1.5 times theoretical oxygen. In the last example of methane we had seen, let's say if I am supplying 100 moles of methane, then the theoretical amount which is required is, for 100 moles you require 200 moles of oxygen. Okay, now that is going in 50% excess. So let's say I have calculated my theoretical oxygen as say 200. So now I am supplying 300 moles of oxygen. So for the last example which we had seen, if I am saying 50% excess of oxygen, that means I am supplying 300 moles of oxygen. So the calculations are very simple. Okay, if you have theoretical amount, you can easily find out what is the oxygen which is fed. One more thing you have to keep in mind, that your percentage excess of O2, that will always be equal to your percentage excess of air. Keep this in mind. If percentage excess of O2 is given, don't waste your time in calculating what will be the percentage excess of air. They will be one and the same. Okay, it is a matter of simple ratios, so that will cancel out and you will get the same percentage excess of air. So these are some things which you have to always keep in mind when you are doing material balance which involve combustion reactions. Okay, so in this video we had taken some important points which you have to keep in mind when you are doing your material balance on combustion reaction. How do you go from wet basis to dry basis or dry basis to wet basis? How do you calculate theoretical oxygen which is required? And also you have learned what do you mean by percentage excess of oxygen which is used. So I hope that you will find this video useful, and if you like this video, please hit the like button and subscribe to my channel, and thanks for watching. Thank you so much.